Hello everyone. In this video, we will discuss about chemistry of lanthanides, what is lanthanide contraction, what is the cause of lanthanide contraction, and what are the various consequences of lanthanide contraction. And we will also discuss about the various applications of lanthanides in different areas. But before going to discuss, now let us discuss what are the learning outcomes of the present video. So after studying this lecture, you shall be able to explain or understand the inner transition elements, which is also referred to as rares. You also know the physical and chemical properties of lanthanides. You can also understand the lanthanide contraction and its consequences. And at last, you also know the application of lanthanides in this video. Now come to the slides in which we will discuss about what are inner transition elements, that is also known as rare earths. So the elements which have partially filled with n-2 f orbitals are referred to as d block and f block elements, since their inner subshells, that is 4f and 5f, are successively filled with the electrons. So these elements are also referred to as transition elements. So on the basis of that series, there are two series of inner transition elements, and these are: first is the lanthanide series, which belongs to the 4f block elements, while second series is known as actinide series, in which we have 5 block elements present in this. Now let us discuss about the position of lanthanides and actinides in periodic table. As we can see, this is the modern periodic table. In this case, we can see that these single star, double star represents the position of lanthanides and actinides in the 6th and 7th period of the periodic table because of shortage of space in this period, because they have discovered later on. That's why we have put these elements, that is lanthanide series and actinide series, on the bottom of two horizontal rows, which is starting from lanthanum to lutetium, that is 57 to 71, and total for 15 electrons, 50 elements. Yeah, we can say in case of lanthanide series there are 14 elements are present. Similarly, in case of actinide, which is starts after actinium, that is the 89, start from this one, and the lawrencium, that is 103 atomic number. So this, basically it is starting from the 90 thorium and ends at the lawrencium 103 element. So this is the position of lanthanides and actinides in their periodic table. Now come to the what are lanthanides, how we can define lanthanides. So basically, now lanthanides are the rare earth elements of the modern periodic table, that is the elements with atomic number 58 to 71. These are the following the elements after following the lanthanum. Lanthanum atomic number is 57. So after that we have 14 elements from 58 to 71, as we have seen in the previous slide. They are normally referred to as lanthanides, and they are also referred to as rare earth metals because the occurrence of these elements is very small in earth crust, that is of only 3 into 10 4% of earth crust. And the term lanthanide was first introduced by Norwegian mineralogist, that is Victor Goldschmidt, in the year 1925. So that is given by this scientist. Then after that, the lanthanide family, it consists of 15 metallic elements that starts from lanthanum to lutetium, all but one of which are F-block elements. And further, the elements in which the additional electron that enters into the n-2f orbitals, these are called as inner transition elements, in which the valency shell electronic configuration of these electrons that can be represented as general is, that is n-2 f 0 to 14 electrons, n minus 1 d 0 to 1 electron, ns2. This is a general electronic configuration for this inner transition elements. The valency electrons of these elements lie in the 4f orbitals of most lanthanide series, And the 4F inner transition elements, these are also known as lanthanides because they come immediately after the lanthanum. And 5F inner transition metals, these are known as actinides because they come immediately after the element actinium in series. And the lanthanides are highly dense elements with density ranges from roughly 6.1 to 9.8 grams per cubic centimeter, and all of these are known to form Ln3 plus type of cations. Now come to discuss about what are the physical properties of different lanthanides. So lanthanides are metals which are having white silvery appearance. They are relatively soft, but each element gets slightly higher as the atomic number increases in the periodic table, since they are still malleable and ductile in nature. And they are also soft metal which can be easily cut with the help of knife. Another property, that is they have very high melting point and boiling point, and they have different reaction tendencies depending on their basicity. Some are very reactive in nature while some take time to react with the other compound. And lanthanides can be corroded or become brittle if they are contaminated with the other metals or non-metals present, and they are also mostly form a trivalent compound, sometimes which is called as divalent or tetravalent compound. They are magnetic in nature and good conductor of heat and electricity. So these are the physical properties of lanthanides. This is the image for which shows the ytterbium having atomic number 70, which is obtained from the earth crust. Now come to the electronic configuration of different lanthanides. So as we can see, these lanthanides, they are starting from the lanthanum element and it ends on the lutetium, that is La2Lu, which starts from the atomic number 57 and ends at the atomic number 71. So this is the general electronic configuration. This is the electronic configuration for all, in which we can see that valence electron filled in the case of F4F orbital. That's why these are referred to as inner transition elements, and they are in the 4F block series in periodic table. So as we can see that electron is continuously increasing because in this case we have for lanthanum we have xenon, that is noble type gas, 6s2 5d1, and we can write in case of 3 plus oxidation state we can write xenon 4f0 whose radius in picometer is 116. Similarly, as we are moving down, we can see that valence electron is entering into the F shell in this case. So that's why on the base of this one, they are called as lanthanide series. Now discuss about chemical properties. So we have different chemical properties. When metal combines with the hydrogen, they gently heat it in the gas, and the carbides, that is Ln3C, Ln2C3, Lnc2 are formed when the metals are heated with the carbon, and they liberate hydrogen from the dilute acids, as we can see here, and burns in the halogen to form the halides. With halogens, they are forming the halides. With the water, they are forming the hydroxides, which is basic in nature. With the carbon, they are at higher temperature. When we are heating, we are getting the lanthanum carbonides. When we are heating with the nitrogen, we are getting the nitrogen compound. And when we are heating the lanthanides along with the sulfur, we are getting the sulfides of the lanthanides. And when we are burning in the air, so we are getting the oxides of these lanthanides. They form oxides, hydroxides of type M2O3 and MOH comprise, which is basic like alkaline earth metal oxides and hydroxides. Now, let us discuss how we can define lanthanide contraction. What is lanthanide contraction? So basically, if the atomic size or ionic radii of tri-positive lanthanide ions that decreases steadily from the lanthanum to the lutetium in the periodic table from left to right position, due to increasing effective nuclear charge and electron entering in the inner n-2f orbital. The increase in effective nuclear charge pulls the electron closer to the nucleus. This gradual decrease in the size with an increasing atomic number is called as Lanthanide contraction. Now, what is the cause of lanthanide contraction? So, in lanthanide, atoms and ions, the 4f orbital is filled successfully from cerium to lutetium, and in general, the shielding effects of electrons is decreases in the order ns, then np, then nf. How we can express this one? It is the effective nuclear charge equal to Z, that is atomic number minus this is shielding wave. Now, what are the various consequences of lanthanide contraction? So, in few slides, we will discuss the various consequences of the lanthanide contraction. In this slide, first, the consequence is which is due to the lanthanide contraction, that is the change of basic properties of lanthanide metal hydroxide compound. So we can see that due to the lanthanide contraction, the ionic size from lanthanum to lutetium, as we can see here, is a lanthanum, is a lutetium. Cationic size is having 103 picometer for lanthanum ion, while we are having 86 picometer for lutetium ion. So we can see that cationic size, if ionic size is gradually decreases from lanthanum to lutetium. Similarly, as a result, the covalent property of lanthanide metal hydroxide compound it regularly increasing according to the Fajan rule from lanthanide to lutetium. We can see in this case, if we are moving from left to right, then basic character increasing from this to this side, and we can see that lutetium hydroxide is more covalent than lanthanum hydroxide. Now, with the increasing covalent bond character, this basic property is decreasing from this lutetium hydroxide to lanthanum hydroxide. So we can say that most basic hydroxide among the lanthanide element is the lanthanum hydroxide, while the least basic hydroxide is the lutetium hydroxide in different lanthanide elements. Our second consequence of the lanthanide contraction is mainly the separation of lanthanides. So the property of metals are determined by their size and charge. Since all the lanthanide ions are of about same size and also carry the same charge due to the lanthanide contraction, so their property are also identical in nature. So due to this identical in nature, separation of lanthanides from one another is very difficult. What is another consequence? The difference in the density between the second and third transition metal series. So the density of second and third transition metal series are much more higher due to the lanthanide concentration. Why it is? Because the atomic volume of two different elements of 4D and 5D series with the same group is near about, but atomic mass of 5D series elements become much higher. So due to this one, there is a difference of density between in the second and third transition metal series. Now, another consequence is occurrence of yttrium with heavy lanthanides. Then we can see that the crystalline radii of yttrium 3 plus and francium 3 plus are basically equal in nature. As we can see, yttrium 3 plus is equal to 0.88 angstrom, while europium 3 plus it is having 0.88 angstrom. So this similarity in the ionic size of these two cations coupled with equality in ionic charge equal to plus 3 oxidation state in the both ions, which accounts for invariable occurrence of ytterbium with the heavier lanthanide. So this marks the similarity in between them in the crystal structures, chemical property, solubility between ytterbium compounds and the corresponding compounds of the heavier lanthanides make it difficult to separate ytterium from the heavier lanthanides. It is because of this similarity that ytterbium is regarding as for all practical purpose as a member of lanthanide series. Next consequence is complex formation. Because of smaller size but higher nuclear charge tendency to form coordinate is maximum in case of lanthanides. So they are forming the complexes and complexes increasing from lanthanum 3 plus to lutetium 3 plus in due to the lanthanide contraction. Now, what is another consequence? The decrease in chemical reactivity of next transition elements on the lanthanide. We can see that due to the lanthanide contraction, the ionization energy which is required to remove an electron from the elements in gaseous state of the next on the lanthanide element, it increases. Hence, their chemical reactivity decreases due to the increase in the ionization energy. For example, the chemical reactivity of the elements which belong to 6 period such as gold, platinum, mercury are very much less. Now, next consequence is similarity in atomic size of second and third transition element. We can say that due to the lanthanide contraction, the atomic and ionic radii of next and before on the lanthanide elements with same group are about same. For example, the atomic radius of zirconium group 4 period 5 and HF group 4 period 6 are about 160 picometer and 159 picometer respectively. Now next consequence is the separation difficulties between second and third transition series elements. So we can see that the atomic and ionic radii of second and third transition series elements are identical to each other due to the lanthanide contraction. So due to this result, their physical and chemical properties are similar to each other. That's why separation of second and third transition elements from each other are very difficult. For example, separation of zirconium from HF is very much difficult due to the lanthanide contraction. What are the various applications of lanthanides? So, lanthanides have various applications in different areas. Some of these we have discussed in this slide, like they can be utilized for metallurgical applications. Some of the alloys of lanthanide elements they find important metallurgical applications like reducing agents. Examples are mixed metals like in which we have ceruleum 30 to 35%. Second application is ceramic applications. They can also be utilized for ceramic applications. We can that cerium third and ceramic fourth oxides find use in glass polishing powders, whereas neodymium, that is ND, and praseodymium PR oxide are extensively used in coloring glass and in the production of standard light filters. Another application it can be utilized for catalytic applications. So some lanthanide compounds can be utilized as a catalyst. Examples are cerium phosphate is used in the petroleum cracking as a catalyst. Another application that they can be utilized in the electronic applications. So the ferromagnetic garnets of 3 and 2 O3.5S2O3 5Fe2O3 types are used for microwave devices, and at last nuclear application. These elements and some of their compounds are used in nuclear control device, shielding devices, fluxing devices like we have strontium, europium, gadolinium, etc. are some of the important isotopes which can be utilized for nuclear technology. And oxides of lanthanides can also be useful for phosphorus in fluorescent materials, while ceramic sulfate is a good analytical oxidizing agent. As we in this case, we can see that this lanthanum, which is also referred to as rare earth, it can be utilized in the camera lenses here, amongst other things. Lanthanum is found in the uranium mineral. Similarly, cerium, it can be utilized for sparkling light, also used in the permanent magnets for sparkling light. That is called application of this one. Similarly, praseodymium, it can be utilized for making the parts of aircrafts, while neodymium can be utilized for agriculture purpose, and europium can be utilized for making CFL, while europium, that is having atomic number 63, it can be utilized to produce blue, red, white radiances in the computer monitors and television screens. It can also be utilized for energy efficient light bulbs. These are some of the practice questions that can be solved on the basis of present video. Like we have, why is lanthanum hydroxide is more basic than lutetium hydroxide? What are lanthanide series? How many elements are there in the lanthanide series? Why cerium 4 plus is good oxygen in aqueous, whereas europium 2 plus and ytterbium 2 plus ions are good reducing agents? Size of trivalent lanthanide cations decreases with the increase in atomic number. Explain why zirconium and hafnium have almost similar atomic radii. So these are some of the practice questions that can be solved on present video. At last, these are some of the references which is mainly utilized for the preparation of this video. At last, thank you for your kind attention.